We're going to look here at three different substitutions that are used to solve first-order differential equations. Here I'm going to present the various substitutions, and then in subsequent videos we're going to see them applied in turn. We have here the equation quantity y squared plus xy times dx plus x squared dy is equal to 0. This equation is in a category that we've referred to as homogeneous. It's homogeneous because in each term, all of the exponents add up to the same number. Formally, we would say, given a function f of xy, if we can replace x using t times x and y using t times y, and then fully factor out the t with some exponent, maybe the exponent's 1, maybe it's 3/2, maybe it's 2, times the original function f of xy, then that function is said to be homogeneous. If that property applies to m and n in the differential equation m of xy dx plus n of xy dy equals 0, then the equation is said to be a homogeneous equation. In the example that we're looking at currently, m of xy is equal to y squared plus xy. And so if we replace x using t times x and y using t times y, we can see that we have t squared y squared plus tx times ty is going to be t squared xy. That t squared can be factored out of both terms, giving the result t squared times y squared plus xy, which is t squared times m of xy. Our solving doesn't really have anything to do with the t at all. This is simply a verification that m possesses this homogeneity property. We can see in this case that n equals x squared also possesses that same property, and that t squared is the same for both functions. That puts this in the category of a homogeneous equation. In the case of a homogeneous equation, the substitution is either y equals u times x, or it's x equals v times y. Our choice of u and v is completely arbitrary. That doesn't really matter. And either one of these substitutions would work. In order to see how you would pick between them, let's see how this plays out. In our differential equation, we have m dx plus n dy, and what we have are differentials. And I'm pointing out that they're differentials as opposed to a derivative, say dy dx. The reason I want to point that out is because when we process this substitution, if we decide y is equal to u times x, we need to substitute all instances of y, including dy, which is a differential. So when I differentiate on both sides, I'm going to differentiate using differential notation. On the right-hand side, ux, u should be considered to be a function of x, and so we're going to use the product rule. And so dy is equal to x du plus u dx. In the case of using x equals v times y, we would consider v to be a function of y, so v times y is a product of functions of x. And we would end up with dx is equal to y dv plus v dy. We're either going to substitute y using ux, and so dy is equal to x du plus u dx, or x equals v times y, and so that dx is equal to y dv plus v dy. And I'm repeating that because the substitution is going to go into the original differential equation. And whichever differential we substitute is going to turn out to be in a term that becomes more complicated because dy is being replaced by two terms. If we have coefficient functions, one of which is simpler than the other one, in this case x squared is simpler, I would choose to make dy more complicated because distributing x squared into x du plus u dx is a little bit easier than foiling y squared plus xy times a replacement for dx, which would be two terms. Again, we'll get into all that in my example video. For now, we're going to move on to the next type of equation. We're looking at dy dx minus y is equal to e to the x times y squared. We can see that it looks linear except for the y squared term. And a function that looks linear, dy dx plus p of x times y equals f of x times y to the n. An equation that looks linear except for a power of y, such as in the case of dy dx plus p of xy equals f of x times y to the n, is called Bernoulli's equation. In this case, the substitution is u is equal to y to the 1 minus n, where n is the power that we see on y that's making the equation not linear. In this case, we have n is equal to 2, and so u is equal to y to the negative 1. We're going to solve for y. In this case, that means finding the reciprocal of the left-hand side, so y equals u to the negative 1. And in our equation, dy dx is a derivative. So when I substitute, I want to use derivative notation. Dy dx is then equal to the derivative of u to the negative 1 using the power rule is negative 1 over u squared, but u should be considered to be a function of x. So we have a chain rule, du dx. So we end up replacing a derivative with an expression that also contains a derivative. We'll see how the rest of this plays out again in the example video. The last type of substitution is pretty straightforward to identify. We're looking at an equation of the form dy dx is equal to f of ax plus by plus c. That's a linear combination of x and y plus a constant. And we can convert it to a separable equation. The substitution is simply u is equal to ax plus by plus c. And we can see that making that substitution gives us that du dx is equal to a plus b dy dx, differentiating all the terms with respect to x. We again have a derivative in our equation, dy dx, and therefore when I substitute, I want to use derivative notation. And then we'll see here that we can solve for dy dx, giving us dy dx is equal to du dx minus a all times 1 over b. We're going to handle this a little bit differently than we are in the symbols here. And in the case of the example I have here, dy dx equals 3x plus 2y over 3x plus 2y plus 2, we might say that u is equal to 3x plus 2y plus 2, what we see in the denominator. And then du dx is equal to 3 plus 2 dy dx, and then solve for y. Again, we'll see how that plays out. You know what I'm going to say in the example video.